Welcome back. So this is session 13, time series analysis, and in this video we are going to discuss how to deal with the time variables in machine learning. Till now, whenever we are talking about the influence of something, we talk about independent variables and dependent variables. But there are times when we need time variable, but we don't know how we can add that into our data set till now, right? For example, stocks get influenced by few things. But the most important variable for the stocks get influenced is always time. Like you cannot compare the Bitcoin market in 2011 to 2025, right? So that's where we have a tool called time series analysis. Now, time series analysis is heavily influenced by linear regression. So basically, what models we are going to talk about here today are going to be some variant of linear regression model specifically designed for time variables. In this video, we are going to talk about AR, autoregressive, MA moving average, and ARIMA models. And for this particular thing, we are going to use package stat models. And stat models is basically a package that basically deals with all statistics related models. It also contains functionality for linear regression model as well. These are some imports that we always have to make whenever we're using something in Python. And now here we are creating a dummy data set, and why we are doing that we will see it now. Now whenever we talk about time series model, we have a curve like this. Like with the passage of time, how does the value change? For example, if we're talking about the Bitcoin, initially it was below something and then it increased and it's increasing till now. But it will not always be the case. Sometimes it reduces, sometimes it can have any kind of shape. But mainly there will be three things that we are going to look for. The first thing is going to be the trend. Trend is basically overall market, is it going up or is it going down? So if we extract the trend from this curve or this time series, we will see something like this, that we started from here and we are here right now. So basically we have an upward trend, right? The second thing that we're going to talk about is seasonality. Every time series can have seasonal component, but it is not always be the true, but most of the time we have seasonal component. Like for example, if you're selling ice creams and in summer your sales increase and but in winter your sales decrease. So this influence can be seen directly in your time series. Like if this is related to your shop data and you're seeing increase in summer and decrease in winter, so that's what you should understand, that you have a seasonal effect on your time series. And if we remove these two, the remaining thing that will be irregular component, or we also call it noise. Okay, now when we talk about time series analysis, our data set should be stationary. Now what is stationary? Stationary basically means our main properties like mean, variance, autocorrelation should be constant over time. Okay, if we take a look here, our mean is not constant, it's increasing with time, right? So this is something we call it a bug in our time series analysis. So whenever we have something like that, we need to make sure that this should be consistent over time, and based on that we can use multiple models. And this is called time series analysis. And sorry, stationary series. For stationary series we have different tests, but here we are going to talk about the ADF test. Okay, it's a statistical test. It's a null hypothesis that series is non-stationary, and alternate hypothesis is still series is stationary. And if our p-value from the test is less than 0.05, we can reject the null hypothesis and we can say that series is stationary. And it's quite easier to do. Like all you need to do is just AD Fuller, and here you have to specify the name of your series that you are going to work on. And this function also comes from stat models package. Now if you're talking about the code, let's talk about the code. So basically we created a dummy data set, and for dummy data set we created a trend line. First we generated values from 0 to 100, and then we added trend line and seasonal effect and some random noise. So basically we have a series that contains all type of data set for demo purposes. This is just one way to plot it. So basically we created three separate plots and then combined them. The original one, the trend one, the seasonal one, and the noise one. Sorry, four separate plots, and we just combined them. And for the combining them we are using access dot zero, that on the zero it should be this one. On the initially we defined that we are going to create subplot, it should have four rows and one column. So basically we will have the row wise plots. Okay, and once we defined that and the width and length of every plot, all we need to do is just use the axis 0 for the first plot, axis 1 for the second plot, 2 for the third plot, and 3 for the fourth plot. So basically this is one way to create multiple plots in a single figure. And again it's just simple, you just need to put AD filler and give the name of the time series, and it will just give you an output, a test result, something like this. All you need to do is just go to take a look at the p-value. If it's less than 0.05, series is stationary. If not, it's not stationary. And also you don't need to do the test if all you can see there is a trend line in your series. Okay, I mean trend line basically represent that your mean is not consistent over time, right? And now since our whole time series analysis is dependent on series stationary series, we should understand that how we are going to work on with such a series. Like most of the time in the real world scenario we will have seasonal effect, we will have trends, and we will have all that stuff. So to deal with that we have differencing. Okay, so basically what we do is we take the difference of the series and create a new series from that. And when we are talking about differencing, we basically means that we are going to minus our current value with the previous value. Okay, so all we did is we just subtracted the previous value from the current value to remove trend and seasonality. Also we can also introduce degree to that. Like if we are using first differencing, basically we are trying to remove linear trend from our series. If we are using second differencing, we are trying to remove quadratic trends and all that. But most of the time you have to apply it for the first time, you just apply it, you take the test again for test stationary, and here you will get the new results. Now here we are using test stationary because we modified our ADF filler test. Okay, we just create a wrap up, a new function for that that uses same test and show the output in a cool manner. But you don't have to do that most of the time. All you need to do is just use this here, and in it you just need to name it. Since we defined this particular function, now what we are going to do is we are going to take the test, show the results. Based on that, we will write an interruption that series is stationary or not. If it's less than 0.05, we say series is stationary, and if it's greater than 0.05, it says series is non-stationary. Okay, and we will also add a visualization that basically going to show rolling mean and rolling standard deviation. And why we are doing that? Because we need consistent rolling mean and consistent standard deviation for a series to be stationary. So this is just a wrap up around the filler test, so we get better looking results. But if you just instead of here writing test stationary, you write ADF filler and run it, it will work the same without visualization and without all that cleanup. Now we again run the test and we are getting a p-value 0.0000 something. Basically it means this is what we are looking for, and our cheese is stationary. And now if we again create the plot, we can see that we have a rolling mean and rolling standard deviation that basically is consistent over time. So we are not seeing upward or downward trend here. Now let's talk about the first model that we're going to talk on today. It is AR model. Now we remember linear regression model. Linear regression model helps us to understand that how we can model a relationship between dependent and independent variable. But the thing is, here we are going to talk about the time, and we are going to treat time as our independent variable, right? And how we can do that, let's talk about that. The first equation is from the linear regression, where y is equal to beta naught, beta 1, x1, x1, x2 are independent variables and y is our dependent variable. But in this particular case, we instead of beta naught, beta 1, we will have c, phi 1, phi 2, again the constants that we are going to estimate. And on x1, x2, we will have yt minus 1, yt minus 2, yt minus b. Now, yt is basically the current value of stock at current time. Yt minus 1 basically means what its value was in on the previous timestamp. Like if you're talking about the hourly data, if at current time at 10 a.m. it is this particular value, what it was on the 9 a.m. Okay, and in the same manner we will have t minus 2, t minus p, and all that. Now if you talk about it, it's just a linear regression model, but instead of x1, x2, we have past values of the same series, and we have coefficients that we're going to estimate and that we're going to influence. Now here we added t minus p, so basically we want to say that we can get lags as many as we want. Like we can create a model based on only the previous value. We can also create a model based on previous two values or previous p values, and that's why we are getting AR into a p here. So basically it's the order of our model. Okay, for example, if we are talking about in simple terms, now we have a stock and we have lost 10 values for it, and I'm just taking a simplest case possible. For example, we have values like 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these are the last 10 values for our stock. We can take it as an every time update or as an every hourly update, but this is not the point here. Okay, and we are trying to create AR1 model. Okay, and when we say AR1 model, we basically mean there will be only phi 1 and yt minus 1, c plus this, and these terms will vanish, right? What our dataset will look like? Our dataset will look something like this: x and y. Now x is going to be independent variable and y is going to dependent variable. If when it was 1, our dependent variable was 2, and when it was 2, our dependent variable was 3. When it was 3, our dependent variable was 4. So that's basically what our dataset will look like for this particular model. Okay, and if we are talking about AR is equal to 2, then we will have x1 and x2, and we will see 1, 2, and here we will see t. Okay, and in the same manner we will have 3, 4, and again y will be 5. Basically, we are using previous two terms or previous one term as our independent variable, and we create a column out of it, complete column. Again, a complete column for second lag if we have our dependent variable. Now, once we have a data set in this particular format, all we are going to do is just using a linear regression model. Now, let's talk about a simple case where we take y1 and y2 here, and we estimated the equation, and it's like y of t is equal to 0.7 minus 0.3 plus our noise. So if we visualize it, it will look something like this. And this is what we call AR2 process for this particular data. Again, we can just test it out. We can test our theory that these two models are same with a different data shape. All you can do is you can just use direct functions, the predefined functions that we have in stat models package, and you can just use simple linear regression by creating the model, and you will see that you will get similar results. And this is exactly what we're doing here. Here we use the predefined function create AR feature. Basically that's based on data styling, like we created x1 x2 for our data set, and we applied linear regression on it. And when we compare the result based between these two, we can see that we will have similar looking equations. Like here we have coefficient of 0.65, here we have coefficient of 0.70, minus 33 minus 30, 0.04, but here 0. So there is a minor difference in these two equations, but in theoretically speaking they're equal, or they're on the same page. And why we are saying differencing? Because when we talk about predefined functions, like we are talking about linear regression, they have their own style of code that basically do some kind of an operations that might be different from the other, but in theory they are going to be the same. Now if we have a series and we plot the series, it will look something like this, the solid red line. And if we use AR2 model to generate the predictions, it will look something like this, the dotted line. So there will be a minor differencing, but I mean these models like that we are talking about, this is classical statistical models, and these are not going to match the performance of deep learning or LSTMs or neural networks that we are going to discuss in the next few lectures. But still they are good foundation to understand about the time series analysis. Now here we have two different things, autocorrelation and partial autocorrelation. Now these are two functions that basically helps us to define the order of our time series. Like for example, if we're talking about the AR, we should understand that what should be the best p-value for our model. Okay, and what how we decided? We decided based on the partial autocorrelation function. And let's talk about that. So we have two different functions, plot ACF and plot PACF. They are two functions that basically plot the autocorrelation of any function and partial autocorrelation. And if we are talking about the AR process, we are going to see the PACF, this one, partial autocorrelation function, and we will see where it cut off. Like this is the lag 0, this is lag 1, this is lag 2, and after that it merged into the confidence interval, so it cuts off on the lag 2. So that's why lag 2 or PAR2 is basically the right order for our series. So this was whole theory about behind the art of regressive models. Now let's talk about the moving average. No, in autocorrelation, or sorry, in autoregressive or AR model, what we did is we defined the new prediction based on the previous data, right? But here in moving average, instead of defining that based on the past value of the series, what we did is we used past error or residual from the predictions. Okay, so basically we did the predictions, and what we have remaining, we take it as our data point. So here we are going to see, instead of y, we're going to see et minus 1, basically the error from the past term. And for to define the order in ACF, in AR model, we look into the PACF or partial autocorrelation function. But for this, in the moving average, we will see the similar style, but within the ACF plot. So what we're going to do is we are going to look into the plot and sorry, yeah, we will have our data, we will have our series, we create the autocorrelation function plot and we look the lag, like here we have lag 0, lag 1, and after lag 1 it vanished, so it should be the 1, and we take only error 1 here. So this should be our model, and we should not include the remaining lags. And when I say lags, it basically means the past values or past errors. Again, we are taking a process, a MA2 process, or an MA2 equation that we're going to visualize and we're going to model. We look at the ACF PCF plot, and based on that, we created the model. Now, these are two different approaches where we talked about the past values and the past errors. But here is a combined model or a better model that contains both of these, and it's called ARIMA. In ARIMA model, we have three parameters instead of one. We have P parameter that comes from AR model. We have a Q parameter that comes from MA model, and there is a D, basically means differencing. So in ARIMA model or in AutoRegressive Integrated Moving Average model, we have AR component like the same AR equation. Got it? And we will have a moving average component, the same MA equation. And the D is basically the differencing or the number of differencing to achieve the stationary. So whenever we are trying to use it, we are going to see that either our data is stationary or not. If our data is stationary, we move on with D is equal to 0, and we investigate the ACF and PACF plot, and based on that we decide the order for P and Q and train our model, right? But if our series is not stationary, we take its differencing, D will be 1, and we look again either series becomes stationary or not. If not, we go with D is equal to 2. No, again the simple model, we in simple models we have linear combinations with past values or errors, but here we will have linear combinations of both. We are generating a data set, and based on that we will try to do predictions using a RIMA model. This is how our data set looks like. It contains some kind of trend in it, and it's not stationary for sure, so that's why we're going to go with the differencing or D is equal to 1 in our RIMA model. We did differencing, we again checked, and now we have p-value less than 0.05, and we are good to go. Once we have that, we will investigate the ACF and PACF plot. From ACF plot, we can see that we will say 1, 2, and 3, and after that it gets inside the confidence interval. So ACF or MA component should be 3, and the PCF. And now here we should see that 1, 2, 3, and from this point we will also consider 3, and we will not move forward with the 5. Also, when we say that we are going to see 1, 2, 3, basically we are adding complexity to our model with every new variable. Okay, and we should also consider that we don't want to go with the bigger values like 4, 5, 6, 7, 8, 9, 10. Okay, now here it choose 1, 1, 1, but instead of 1, 1, 1, we should choose 3 from 3 for MA or Q component, and we should choose 3 for AR component as well. Here it gives the order is equal to 1 1 1, but instead of 1 1 1 we go with the 3 1 and 3. Now I'm using run all because I haven't run the previous codes, and if I run this component or this particular chunk directly it might show us error. So I'm just going to use run all, so everything that isn't required to run this should be added. Now here we will get 3 coefficients for AR component and 3 coefficients for MA component. Why? Because we are using third order, or 3 lag terms, or 3 previous terms and 3 error terms. We can see the significance of each of them based on the p-value. And if we plot this, we use the same machine learning style. We take our data set, we split it into training and testing, and based on that we generated the predictions, right? Like here we have the full data set, we created a train set. It's going to be 80% of the total length of the series, and from based on that we defined that ARIMA series 80% should go to the training size and 20% go to the testing size. So basically we defined a value, an integer value, that if a series has 100 rows, we define that 0.8 multiplied by 100 is equal to, gives us an integer, basically means 0.8 multiplied by 100 is going to be 80. Okay, and in series we are saying that RIMA series we need complete series, but with training, sorry, with all the rows, and with I mean we need, we have 80 rows, sorry, we have 100 rows in our data set, and we define training size is equal to 80 based on this formula. So basically we multiplied 0.8, and now we're going to generate two different things, train and test size. Now what train is? ARIMA series, basically our series, and we are saying colon till train size. So basically means from the start of series to train size, like for example from row 1 to row 80. So first 80 rows are going to be in train set, and again we have a comma, we also have a comma here. So basically it means after this comma we're talking about the test. And in test what we're going to see is from train series, basically means from 80 row to till end. So if you don't write something here, it means from the start, because it's before the thing that we defined, and if it's after, it means till the end. Okay, so that's the first 80 rows or first 160 rows. In this case we have 200 rows of data, so 160 rows goes to the training set, and 40 last 40 rows goes to the testing set. Now this is an approach where we are not selecting random 40 or random 80% into one section and random 20% into different section. Why? Because this is a time series and time is important. Like we don't want to lose the track of time. So that's why we select first few as a training set and last few as a testing set. We run the model, we have the model. Based on that model, we generate predictions, and again, since we defined first 80 in training set, we take the length of training set, like how many we have in the length. Here we have 160, so prediction starts from 160 plus prediction starts from 160, prediction start is equal to length of train, and prediction ends at 160 plus the 40 minus 1. Basically we have a value at 160 that we don't want to add, so that's why we are minusing one value from our series. And we use the model dot get prediction function, basically from stat models, that basically generate the prediction or all these periods. All we need to do is just say start time and end time. Okay, and we can also calculate the mean traces with MSE or root mean square or mean absolute error. all these with the formulas. All we need to do is provide the test and the predictions, and we will get a value. Now, if we want to see the plot or if we want to see our predictions, plt.plot range train. So basically, we define a figure, we plot a data set, our data set with the train, and after that, we plot the test data. Plt.plot. So basically, we plot the test data, and again, we plot the prediction data. We specify different colors so we can understand what's going on. In the first one, we didn't specify any color, so it will go with the default color. In the second one, we specified green color, so the actual data or actual test data will look something like green in the green color. In the last or in the predictions, we use red color, but with the line style is equal to dotted. So instead of a solid line like this, we will get a dotted line. And we also introduce a axis line, and we specify that axis line should be on the length of train, basically means the 160. So we can understand that this is a training set, this is the test results, sorry, this is the test results, the solid line, and this is the actual values. Okay, so that's basically what we can achieve from a ARIMA model. It's a time series model, it's a very basic model, so you won't see it in the working most of the time, but it has its own significance. Now here we talked about the different scenarios, but the things didn't change much. And since it's heavily dependent on the linear regression, so it contains all the traits of linear regression as well. Like we have to do model diagnostic, either the model is appropriate or not. We will check the different assumptions. Again, assumptions are going to be in the same line with our linear regression. So we see that the residual should not contain any kind of pattern, it should provide noise. The histogram should be perfectly normal, the QQ plot should lies on the line, and here when we talked about the ACF plot, it should not contain any significant lags. Okay, so rest of the lags should be inside it, and this is lag 0, so we don't talk about that. Here is another example that you can play with. So that was time series analysis, where we discussed AutoRegressive model, moving average model, and ARIMA model. And this is not it. There are a lot of models. Like we have SRIMA model that basically also account the seasonal effect as well. Okay, and but this is the core foundation of the time series analysis. So that's it for conventional statistical models and machine learning models. In the next session, we are going to talk about purely on deep learning.